Okay, good afternoon. So today we are going to give you some idea about bounds on the code. In fact, I will obtain first. We have already seen two bounds: sphere packing bound and singleton bound. Today we are going to look at Plotkin bound. And before that, I would also like to mention what is the main coding theory problem now. Actually, okay, and and after that we are going to give you idea of MacWilliams identity, which is a very famous identity which connects between the code words, the weight of the code words of a code C and its dual code. Okay, so let us start this. So main coding theory problem. Okay, so let us assume that we are given a code C, and I am talking in a most general sense. So parameters of the code are NMDQ. What is N? N is the length of the code. Capital M, size of the code, total number of code words in C. D is the minimum Hamming distance, and the code is over the finite field FQ, GFQ. Okay, we can define what is known as rate of a code. Rate of the code C is defined as log Q base capital M divided by N. Okay, this is the rate of a code. For linear code, we know that capital M is Q raised to power K. So this formula simplifies to rate of C is nothing but K by N. K is less than N all the time because K is a message symbol and is the total number of symbols. So we know that rate lies between 0 and 1. Now, good code will have high rate. Normally if close to 1, that will be very good code. And sometime, for the practical purposes, people prefer also rate half code. Those are also very interesting codes, and many interesting codes are rate half codes. So this is the basic thing. Now the problem, that main coding theory problem, says that find codes with large rate, R, so I can call it R, okay, or R. So if rate is high, so this is for efficiency, right? And large D. D is the minimum Hamming distance. So if D is large, we know that we can, if minimum distance is D, we can correct D minus 1 by 2 errors. D is large, we can correct many errors. So this is your basic objective for any code. If you want to construct any code, you need to have codes with high rate and high minimum distance. So many times these are bit conflicting statements. So we define a function actually. So suppose our alphabet is size q. Of course, we are looking at finite field, and given values of n and d. So suppose alphabet is, we have given alphabet of size q. Q is greater than 1. Okay, and we are given the values of n and d. N and d is given to us. We can define what is known as aq and d. This function aq and d. What is aq and d? Is maximum number of code words, capital M, such that there exist an NMD code over alphabet A, right? A is our alphabet of size K. Normally we take alphabet to be finite field with few number of elements. Okay, so we are maximizing total number of code words. Okay, when we maximize A, essentially if it is a linear code, we are maximizing K, right? And when we are maximizing K, that means we are maximizing the rate of the code. Okay, so this is a very important function, and the value of this function is known in many cases, and we can say that a code is optimal if cardinality of C. We can say that a code C is optimal if cardinality of C is AQ and D, the maximum possible. Okay, then optimal. This is a very, very important and fundamental parameter. So, so as I told you earlier, I'll just mention briefly these bounds. Again, the first bound that we obtained was singleton bound. We talked about it briefly earlier. We proved it using parity check matrix. So if C is a NKD code, linear code we are talking about. Okay, if C is this code, then D cannot exceed n minus k plus 1. This is a very important bound known as singleton bound. Okay, this is something we already discussed. Now I am going to discuss another very important bound. We already talked about sphere packing bound, so I am not mentioning it here. Plotkin bound. So these bounds are relationship between the parameter KD, so they are really useful. So a code is optimal if it meets one of these bounds, with equality. So Plotkin bound. Plotkin bound can be stated like this: for any NMD code C for which n is less than 2D, we have total number of code words capital M cannot exceed 2 times D divided by 2D minus N. So this is the bound on the total number of code words. It's a very interesting bound, and normally codes which meets this bound are can be constructed from Hadamard matrix. So we'll talk about that after this. So now let me try to prove it. So we consider this summation, double summation. U in C and V in C, where distance between U comma V. Look at this summation, double summation. Now we know that if U and V are two code words in C, then so we know that if U and V are code words in C, U and V are in C such that U is not equal to V, the distance between U comma V will be at least D, because D is the minimum Hamilton distance, right? So this implies that this double sum will be at least M into M minus 1 into D. Because if distance is at least D, I can substitute it here and then vary U and V, right? So summation will vary M into M minus 1 times, we'll get D, right? So this is our first relationship, or I would say a lower bound on the summation. Second, I write down all the code words of A as matrix, a larger matrix of size capital M cross N. Total M code words are there. And let us look at a particular column, say ith column here. Ith column. Okay. So now I would like to see, how much ith column contributes in this sum. Basically, if we assume that in this column there are xi zeros are there, then m minus xi ones will be there, right? So now this 0 1 and 1 0 occurs in pair, actually we know that. So this will contribute this sum will be summation I is equal to 1 to n, because we can do it for each column. From I'm picking up one particular column I, and ith column will contribute 2 times xi into m minus xi to this sum. Okay, so this sum can be computed like this. So summation I is equal to 1 to n 2 times xi times m minus xi. Now I would like to know the answer when this sum is maximum. For what xi this is maximum? Okay, and it turns out that so I can just write down again the sum for you here. Double sum is summation I is equal to 1 to n 2 times xi capital M minus xi, and when this sum is maximum. When this sum is maximum. So I will make two cases. In fact, I will just prove one case. Case 1, when m is even. Then you can sum is maximum when xi is equal to m by 2. Okay. When xi is equal to m by 2. So sum will be less than or equal to its maximum, which is half times and m square, because we can substitute xi is equal to m by 2 in the. Now we know that the lower bound to this sum is, we just computed from first equation, that m times m minus 1 times t, and hence we have m times m minus 1 into d cannot exceed half n into m square. Simplifying this inequality, we arrive at that capital M cannot exceed 2d times 2d minus n. Now, since m is even, we can write it in a much better form that m cannot exceed 2 times d over 2d minus n. Okay, so we arrived at our result, what we wanted to prove. Case 2, I leave it as an exercise for you. When m is odd, so maximum will occur at some other, and you can actually see that same thing. Okay, so case 2 is as an exercise for you. Okay, so finally we have that capital M cannot exceed 2 times greater than 0 d divided by 2d minus n. This is known as Plotkin bound. Very interesting, beautiful bound on the parameters of the code. Now, I would like to show you some tables which are made between length, dimension, and minimum distance, and these are really interesting tables. Okay, so this is a website codetables.de, and you can see that here you go to the linear codes, and I can show you, say, maybe binary codes. Look at this table is a binary code. So this table is for length up to 256 and dimension up to 256. On left hand side the length is given, on right hand side dimension is given, right? So that means if you look at length is 9 and distance is, dimension is 3, you know that the maximum distance possible is 4. So if you click here, and you can see that lower bound and upper bound is 4, this code is optimal. So 9, 3, so 4 is optimal. So distance is 4. And how we construct this code, I mean, there are constructions given here with references, so you can check those things. Now clearly there is exact value given, you can see up to this, but in the table you can clearly see that this is the case when n is equal to 32 and k is equal to 14. We don't know what is the value of distance. Distance is lower bounded by 8 and upper bounded by 9. So we don't know whether it may be 8 or it may be 9. You have to find the exact value. This is a good research problem. Similarly, 9 to 10, this is open case. 6 to 7 is open case. This 6 to 7 is open case. 12 to 13 is open case. All these are open cases. So if you go a bit further, you can see more upper and lower bounds are given. These are the exact values, but here you can see that any one of them, lower bound is 12 for the distance and upper bound is 13. Okay, and how the construction is given, that is also known. So this is a case which is, we can construct codes. So these are the tables, and you can see if you go further the bounds are more, they have lower and upper bounds rather than the exact value. Okay, and similarly we can see the ternary codes table. So you see that here even at a smaller case we have the value 9 to 10. This is not known. Okay, lower is 9, upper is 10 for the distance, and so cases are given here and so on. So this is really nice thing. You can also want to check one particular, say n is 24 and k is 12. So we can see that what code we get? 24, 12, 8. And actually, this, this follows the upper bound and lower bound. So it's a quadratic rescue code. We'll talk about it later on. So, so an exact code is available. In fact, this is extended Gole code. Okay. So it's an optimal code. So by two ways you can check the entries, by entering the values here, or essentially, by looking at the entire table. Okay. So now fine. That's all for these bounds. Okay, so now we look at another important concept, and that concept is the idea of weight enumerators. So suppose C is our NK Q linear code. Okay. So weight enumerator of a code is a polynomial which actually summarizes the entire weight distribution of C. WC of Z is defined as summation I is equal to 0 to n AI Z raised to power I. What is AI? AI is total number of code words of weight I in C. Okay, so this is known as weight enumerator. Now this summation is from I is equal to 0 to n AI, and actually we can, so basically what I can say that WC of Z is nothing but A0 plus A1Z plus A2Z square plus dot 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 an Z raised to power n. You can also write it down. Another nice compact formula is WC of Z can be written as summation x belongs to C, okay, Z raised to power weight of x. Right, so now you see that if weight of x is, there will be one code word, so that is A0. Obviously, how many code words are there? Then if weight of x is 1, how many code words are there? Suppose A1, right? So A1 will come and so on. You can expand it like that. It's the same thing. Let us see some examples here. Suppose C is a code 000, 011, 101, 110, and fuel code is, we know that 000, 111. So WC of Z is 1 plus 3Z square. This denotes how many vectors are there of weight 2, which is 3, right? So this is the thing, 1 plus 3Z square. And similarly, WC perp of Z 1 z cube, right? If C is a code word like C is a code like 0011, we know that C is self-dual, right? So then WC of Z is same thing as WC perp of Z is same thing 1 plus Z square. Okay. So this is a weight enumerator polynomial. This describes a complete weight distribution. Okay, it captures the complete weight distribution of the code. Now, now I want to actually give you a very nice formula. So, somehow we would like to know, if we know WC of Z, can I find WC perp of Z? This is a nice question. So can I ask, is it possible to find WC perp of Z from WC of Z? And the answer is yes. And that can be done by what is known as MacWilliams identity. So I can write down the formula first, and then we will try to prove it. This result was obtained by Mrs. MacWilliams. MacWilliams identity. So what it says that WC perp of Z is nothing but 1 over 2 raised to power n minus k 1 plus z raised to n WC perp of 1 minus z divided by 1 plus z. Okay. So sorry, this is let us see how it prove it. So we'll prove it using certain lemma, and in fact we require 3 lemmas in order to prove this. The first lemma is lemma 1. So suppose I'm going to prove it for binary case, and I think the result extend for query. Suppose C is your nk2 code and y is a fixed vector in f2n. Fixed vector such that y does not belong to C perf. So C is a binary linear code of length n and dimension k, and y is a fixed vector in the space, but it does not belong to C perf. Then inner product of x with y is 0 and 1 equally often. As x runs over C. As x runs over C means x is a code word in C, right? If you vary and take the inner product with this y, it will be either 0 or 1 equally often. So, how to prove this? Suppose A is our set, all those code words x in C such that inner product of x dot y is 0. Y is fixed. Remember, y is fixed vector which is not in C part. Okay. And suppose B is a set, all those code words x in C such that inner product of x dot y is 1. So our target is to show that cardinality of A is same thing as cardinality of B. Okay. So so now what we do? So our claim, we can say that our claim is that cardinality of A is same thing as cardinality of B. This is what we want to show. So let U be an arbitrary code word in C such that U dot Y is 1. This certainly exists. So U exists since Y does not belong to C perf, right? So we know that it does exist. Then we form the coset U plus A, which is U plus X, such that X belongs to A. Now our claim is that again that U plus A is a subset of B. For if we take a typical code word, so for if X belongs to A, then we consider U plus X inner product with Y. What is this? This turns out to be U dot Y plus X dot Y, right? Now U dot and X dot Y is 0, so this thing is 1. So U plus X belongs to B. Therefore, we arrived at this, that U plus A is a subset of B. Similarly, we can show that U plus B is a subset of A, and therefore cardinality of A is same thing as cardinality of U plus A is same thing as is less than or equal to cardinality of B, because that is a subset of B is same thing as cardinality of U plus is same less than or equal to cardinality of A. And so cardinality of B is same thing as cardinality of A, right? So our this inner product runs equally often. This is proved. Okay. Next lemma is lemma 2, which says is a to n. Consider summation x belongs to C minus 1 raised to power x dot y in the inner product x dot y. This value is 2 raised to power k if y belongs to C perf, and 0 if y does not belong to C perf. Okay, this is a simple proof. If y belongs to C perf, then what will happen? This implies that inner product of x dot y is 0 for every x in C. Okay, and this sum, and how many times? The cardinality of C. So in this case, summation x belongs to C minus 1 raised to power x dot y will be cardinality of C into 1 is equal to 2 raised to 4k. Right. Now the second case, we know that x dot y is equal to 0 or 1 equally often, right? As x runs over C. So this implies that the inner product x belongs to C minus 1 raised to power x dot y is 0 using lemma 1. Okay, y are equally often. So this is the case. Okay. Third, we are going to mention now third lemma. Now this time, to let x is a fixed vector in F2. Then, suppose Z is your indeterminate. We have summation y belongs to F2n, Z raised to power weight of y minus 1 raised to power x dot y is equal to 1 minus z raised to power weight of x times 1 plus z raised to power n minus weight of x. So this is really an interesting formula. Okay, we are going to prove it now. And the proof involves actually calculating the sum in two ways. Okay, so first we look at left hand side. Left hand side can be written as, what I am going to do here, I am going to split this summation over each variable. So what I am going to do, so y I can write down as y1 y2 yn, and x I can write down as a x1 x2 xn. y1 is equal to 0 to 1, summation y2 is equal to 0 to 1 dot dot dot, summation yn is equal to 0 to 1 z raised to power y1 plus y2 plus dot 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 yn minus 1 raised to power x1 y1 plus dot 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 xn yn. Wise I have done this decomposition. Now that means, now this portion here I can write down as a partial product. Okay, so overall this quantity will be summation over y1, summation over y2, summation over yn, and it can be written as partial product I is equal to 1 to n z raised to power yi minus 1 raised to power xi yi. Right? Now interchanging partial product and summation, this gives us partial product I is equal to 1 to n summation j is equal to 0 to 1 z raised to power j minus 1 raised to power j xi. Okay. Now this quantity is nothing but, now this summation, this internal summation, the value is 1 plus z if xi is equal to 0. If xi is equal to, this will be 1 plus, right? Remember, if xi is equal to 1, this will be 1 minus z. So overall thing will be 1 minus z raised to power weight of x times 1 plus z raised to power n minus weight of x. Okay. So simple calculation, because the partial product is over I is equal to 1 to n. When we do it for each I, we are going to get the weight again. Okay. So this is the formula. We arrive at this. Now I think I am ready to prove the main result. Main result. Okay. So the main result is MacWilliams identity. For bilinear codes. Okay. So what we want to prove, that WC perp of Z is equal to 1 over 2 raised to power k, 1 plus Z raised to power n, WC of 1 minus Z, 1 plus Z. Right? This is what we want to prove. Very famous identity. So now, in order to prove this, consider f of Z as summation x belongs to C. Consider this sum and summation y belongs to f to n minus 1 raised to power x dot y times z raised to power weight of y. Now if we use lemma 3 here, we are going to express fz in two ways. So using lemma 3 first, what we are going to get, using lemma 3, f of z is nothing but summation x belongs to C Okay, 1 minus 1 minus z raised to power weight of x into 1 plus z raised to power n minus weight of x. Okay, so this now we can simplify. If we take 1 plus z raised to power n common, so this is nothing but 1 plus z raised to power n common summation x belongs to c 1 minus z divided by 1 plus weight of x. Now remember the formula. This thing is nothing but 1 plus z raised to power n times wc of 1 minus z and 1 plus z by definition, right? On the other hand, so this is case 1. On the other hand, if we can actually compute f of z by reversing the order of summation. Actually, I can write it down as summation y belongs to f to n z raised to power weight of y and summation x belongs to c minus 1 raised to power x dot y. Right. Now again using lemma 3, we know that this value will be when y belongs to c perp, then only we will get the value, right? This is summation y belongs to c perp z raised to power weight of y times 2 raised to power k. So this is nothing but 2 raised to power k times wc perp of z. And so we got the result. So we get this. Okay, by comparing both the f of z value, we get the desired result. Now actually I can also mention the result in the query case, but without proof, of course. So in general, if c is a nk query code and c perp is a code with parameters n comma n minus k, then wc perp of z is 1 over q raised to power k 1 plus q minus 1 times z raised to power n wc of 1 minus z 1 plus q minus 1 times z. This is the general case. So in example, let me show you the example. In our previous example, we saw that wc of z was 1 plus 3z square, right? I can compute from wc perp of z from this formula will be 1 by 4 1 plus z whole cube wc of 1 minus z and 1 plus z. We simplify this thing, it turns out that it is 1 plus z cube, right? So now it's really easy to compute the weight enumerator polynomials. Okay, so I think that's all about MacWilliams identity. So this is the very important identity in general that I have written for you. MacWilliams identity. This is the important result. So MacWilliams identity helps you to find out the weight enumerator polynomial of a dual code. Okay, if weight distribution or weight terminator polynomial for a code C is given, we can find out the weight distribution polynomial of a dual code. Okay, so this is a nice result. I think that's all for today. We discussed about MacWilliams identity and we talked about bounds on the codes. In the next class, we are going to look at the head-bound matrix, and using the head-bound matrix, we'll construct the Gole code. Okay, thank you.